Okay, in this video, we're going to now try to determine the equation of a logarithmic function by viewing its graph. And this first example is actually a non-transformed log function. Or, more to the point, it's a function of this form, where it's just simply y equals log of some unknown base, at least for the moment, x. And notice I can be confident that this is the situation here, because hopefully you can recognize that the y-axis is the vertical asymptote, which is the regular feature of a non-transformed logarithmic function. And the other main feature, or I guess common feature of untransformed or non-transformed logs is a x-intercept at 1. The order pair 1 and 0 seems to be present here. So that's all evidence that there's no translations at all, and we just have a log base b of x function sitting in front of us. And the next thing to keep in mind is, of course, this ordered pair, 4 and 1. So if we input 4 in this log function, it's outputting 1. So how does that help us? Well, I think we'll actually just algebraically determine what the base is and then go back and hopefully just try to reason our way through it without the mechanics of the algebra, but it's not terribly intense. If I input 4 and I'm supposed to get an output of 1, then of course that would mean my y value is 1 in this log, even though I don't know the base yet. And of course, how did I get the output of 1? Well, I inputted 4. And that would mean that this base has to match this 4. It's the only way that this is going to be a log that outputs 1, because remember, if you have this property of logs, that if you have log base b and that base gets repeated in the input, that always has to be 1, and that's because b to the power of 1 is equal to itself. That's one way of recognizing what's happening here. Now, of course, you can also just put this in exponential form, that this is a base b exponential to this power of 1. Remember, the log is the exponent, and that all has to equal the number that was inside our logarithm. Of course, that's a pretty easy exponential equation. That would mean the base here has to be 4. So we've actually decoded what this equation is of this log. We'll write that down first with maybe get rid of this with a bigger eraser here. That would mean that this equation would have to be y equals log base 4 of x. And again, probably the fastest way of recognizing your base, and probably notice that 4 is here, and note the location of the y value above that x value of 4 is of course 1. That means if you can identify 1 unit above your x-axis, right, as a y value, where does that happen? Well, if it happens at 4, that means your base is 4, which is a way of, I guess, visually identifying your base instead of relying on the algebra. Okay, our second example here, I think the first thing we should recognize is that the vertical asymptote is no longer the y-axis. Of course, that is located at -2, so that's evidence that we have a function that's been translated 2 units to the left. And I guess another thing to recognize that if the the x-intercept used to be at 1, if we translate that 2 units to the left, that seems to coincide nicely with this graph here, which I guess is evidence that we have no up or down translations for this function. Okay, and the other thing, I guess, other way of recognizing that, if we look for that magical distance of 1 unit from our vertical asymptote, we can see that it occurs here, which of course is an ordered pair that's right on our x-axis. And that's, again, further evidence that we have no up or down translations. So we'll just undo that. I think I'll highlight this x-intercept. So since that spacing of 1 unit away from our vertical asymptote is on the x-axis, that all checks out. And we have a function, at least potentially now, that is y equals log, with an unknown base of x plus 2, which of course translates at 2 units to the left. And we don't want any up or down translations, because that'll mess up our x-intercept of -1 that we have here. Okay, and of course, to finish this off, we can use the ordered pair 3 and 1, which is the other point. It's clearly labeled here, included in our graph. So that would mean we want to output 1 when we input 3. So that'll give us 1 equals log base b of 3 plus 2. So that would mean 1 has to be equal to log base b of 5. And the only way this is going to work is that if that base is exactly matching that input of 5. So that tells us that our base here has to be 5, or quickly we could switch to exponential form to conclude exactly the same thing. So that would mean our final equation here, I guess I can just put a therefore, of this function is y equals log base 5 of x plus 2. Okay, in example number 3 here, we have more transformations to worry about. But first and foremost, I think it's always a good starting point to recognize that your vertical asymptote is not the y-axis. So we have a function that's been translated left and right, specifically because at minus 5 is our vertical asymptote. This function obviously was translated 5 units to the left. And the next piece of the puzzle is to try to identify that ordered pair that's 1 unit away from your vertical asymptote. And I guess because there's only 2 ordered pairs really labeled here, it probably makes sense to at least start here. But notice that is a spacing of 1 unit from the vertical asymptote, which is where our x-intercept usually is if we had this function, if it hadn't been translated left or right. So by identifying the spacing of 1 unit, and the fact that it's not occurring right on the x-axis, but it's 2 below the x-axis, believe it or not, means our x-axis used to be here, which is what this dotted line represents. It's like our pretend x-axis, if you will. And that occurs at minus 2, which means this function has also been translated down 2 units. So let's at least put those 2 pieces of the puzzle together. So right now we have a function that's log the unknown base b of x plus 5 minus 2. So the plus 5 probably makes sense. That lines up our vertical asymptote. The next thing to keep in mind is that spacing of 1, which is our original spacing, remember, of our original x-intercept. Since that occurs at minus 2, it means we have to translate this function down 2 units as well. So let's get rid of our pretend x-axis label. It's not really that's mathematical rigorous, but anyway, it works. Now we can go ahead and use our other ordered pair here, which is negative 1 and 1. We can input that information into this function. So if y is 1 when x is negative 1. So that would mean 1 equals log base b of negative 1 plus 5 minus 2. So if we solve this equation, or at least try to simplify it before we try to solve it, or I guess deal with it is probably a better word right now. Minus 1 plus 5 is 4, and then we have a minus 2. So let's add 2 to both sides. We'll get 3 equals log base b of 4. Now this is a more difficult situation than the first 2 examples, because of course we were getting 1s over here, and then all we had to do was realize that the base has to be that number that's inside this logarithm. Well, that's not the case here, but we can still salvage this by putting this in exponential form. This logarithm is base b, so that would correspond to an exponential with base b raised to this power of 3, and that has to be equal to 4. And we get a base, which is kind of messed up, to be completely honest with you. If we take the cube root of both sides of this, we actually have a base that's mathematically correct, but I think most people would look kind of strangely at you if you used a base that's a cube root of 4. Well, what did we do wrong? Well, we didn't really do anything wrong. We just actually, if you've noticed in the past couple of examples, we've been not worrying about any transformations other than translations. Now, this base is mathematically correct, but we can actually write this a little, I guess, a more typical way, using a positive integer as our base, if we take into consideration at least the possibility of some stretches, which actually are present here. We have a vertical stretch, so let's not worry about this right now. We don't have to abandon all of our work. It actually will still give us the correct answer, but if we recognize the distance this point is from our vertical asymptote is 4 units, that's actually what our base is in this situation. So how can we, I guess, salvage this cube root of 4? Well, guess what? We're going to actually just input that as our base for a few minutes, and we will come back to a slightly different way of doing this question. but we can still salvage what we have here as long as we write this down first. So if we do go with a log base b, now our base is the cube root of 4, which is kind of horrible looking, but I can still put in my plus 5 and my minus 2 translations. So if I'm suggesting that the spacing of this ordered pair from the from the vertical asymptote actually is your base, well, if you take my word for it, it probably means we should change this base. So let's try to do that, and it might actually clean this up a little bit. And maybe your inspiration is just, since I have a 4 here, I'm going to use that as my base and see if I can somehow get rid of that cube root. That would be logical as well. So let's switch this to a base 4 log. So of course, remember, we'd use our change of base formula. We'll go base that we want to move towards base 4, top and bottom. The old base goes to the bottom, and the original input goes to the top. And of course, don't neglect your minus 2 translation there as well. And maybe one more step, maybe you can start to see what's happening in that denominator now. But if I write this as a power, we can see that this cleans up nicely. And this is going to set up, I guess, an opportunity to, rethink our approach and see how we can recognize this result maybe a little bit more efficiently. Now on the bottom, we have log base 4 of 4 to the power of a third. So there's two ways of dealing with this. I can take this power of a third and put it right down in front, which I think I will do, and I'll just cross it off. And then we have log base 4 of 4, which of course is 1, so we have division by a third here, which is the same thing as multiplication by 3. So which would mean my equation is going to be, instead of saying it's log base 4 of x plus 5 divided by a third, well, that's the same thing as multiplying that by 3. And then again, don't forget about the minus 2. So lo and behold, notice we have a vertical stretch that's present here by a factor of 3. So I guess that begs the question, how can we recognize that without doing our change of base approach here? And you know, some of you are probably looking at that change of base approach and saying, that's not too serious. I can handle that and get a log with a nice positive integer base. But just, I guess, keep in mind another option would be to look up here. And the hint that we have a stretch, vertical stretch by a factor of 3 is, of course, if we use our, get my pen, if we use this pretend x-axis and we consider the distance that ordered pair is above that pretend x-axis, check it out, this is 3 units. This is evidence that we have a stretch, vertical stretch by a factor of 3. And why is that? Well, remember, if this is my x-intercept and I come over 4 units, I should be going up 1 unit, which is always the placement, you know, to get that y value 1 unit above your x-axis. Of course, you come over the base as your x input. And now since this distance is not 1 unit anymore, it's 3 times that, well, this is where your vertical stretch, or this is how you can recognize your vertical stretch by a factor of 3. And then you could actually just go back up here and say, well, if this is 4 units, maybe I'll just adjust this. If this dot was 4 units for my vertical asymptote, that means my base is 4 units. And then if I recognize my stretch of 3, you can just plop your 3 out in front. Okay, so there's 2 ways of identifying the equation of this function. First, dealing with the kind of horrible cube root 4 base, and then switching to the integer part of that, which of course is the 4 underneath that square root. Switching that base via your change of base formula can quickly give you the equivalent and probably more user-friendly version of this function, which is 3 times log base 4 of x plus 5 minus 2. Also open, I guess, your eyes and your minds to this possibility that if you recognize this is 4 units, point is 4 units from your vertical asymptote, that is your base, and the distance that point is above your pretend x-axis is actually going to be your vertical stretch. Okay, our last example here, we can recognize our vertical asymptote is now occurring over here at 3. So this function has been translated to the right 3 units. we look for our spacing of 1 unit away from the vertical asymptote, and that seems to be occurring here, which of course is at -1. So this function has been translated down 1 unit. And I think we'll opt for probably the less common method here. I'm going to just ignore the possibility of a vertical stretch and see how messed up my base is. And if it's not messed up and not involving roots and whatnot, then we'll just wrap up and be done there. And if it does have a root attached to it, a change of base is all you really need to do to rewrite your equation. And you'll see that some kind of a stretch or reflection would be present as well. So given this information, I don't know what my base is, but I know this function went to the right 3 units. So we need an x minus 3 in our input. And my pretend x-axis is at -1, so we need to move this thing down 1 unit as well. So this ordered pair over here is 7 and -3. So let's just input this information and see what happens. And if we get something messed up like the previous example, then we might have to tinker with that a little bit with the change of base formula. So we need to output a -3 when we input x equals 7. So 7 minus 3 minus 1. So let's clean this up. We'll maybe add 1 to both sides. And then, of course, do that subtraction inside our logarithm, which is going to give us 4. So let's now go to exponential form. This log, written in exponential form, is base b to the power of -2 equals 4. And if we raise both sides to the power of -2, sorry, the reciprocal of -2, I better say -1/2 here. Notice that's going to give me b to the power of 1, which is what we want. And then this is going to give me, I guess unfortunately, 4 to the -1/2, but we can handle this. We can take the reciprocal of 4 and get 1/4. And then raise that to the power of 1/2, which hopefully you recall, that is actually a square root. So if I take the square root of 1/4, it's the same thing as raising that to a power of 1/2. And then root of the top and the root of the bottom means our base really isn't that messed up at all. It's a base of 1/2. So we can conclude that our function here, equation of this function, is log base half of x minus 3 minus 1. And I'm sure you've noticed up until this point, this log function is kind of upside down, right? It's actually the reflected version where it's getting close to the vertical asymptote on the top part of the graph instead of the bottom part. And I'm sure that wasn't lost on you. So let's wrap this up. And I guess one other thing I should remind you of when we get into these fractional bases, there's also another way of writing that as well, where we can write that as a reciprocal base. But let's get this one down here first. We'll say that our log equation would be log base 1/2 of, I guess I can see it was 3 units to the right and 1 unit down. Now remember that little identity that we looked at earlier, that little trick? You could use a change of base here. If for some reason you want to use a reflected version of an integer base, you can do that as well. And if you forgot the trick, fair enough. I think I'll just rely on maybe a little less luck and tricks, and just we can switch this into a different base if we want using our change of base formula. So another mathematically equivalent equation would be writing this as the base 2. And of course, we would have to switch from base 1/2 to base 2 using our change of base formula. And the input stays on the top and the old base goes to the bottom. And I think you can see where this is going. We have log base 2 of x minus 3 minus 1 at the end. And on the bottom, we can see 2 raised to the power of -1. Of course, it's going to create the reciprocal of 2 there, which is 1/2. And that's a horrible place to write that negative. Let's, of course, put that right out in front. So you could also write the equation of this function as a reflected upside down version of the log base 2 of x minus 3 minus 1. And note, I didn't bother searching out for reflections or stretches or anything. Might be something you want to entertain. But notice, I think once you recognize your two translations, sub in your other ordered pair x and y, and if you get a pretty common base, a base of a half is definitely more than acceptable as a logarithm. And if you want to go maybe the extra mile, you could rewrite that as a minus reflected version of the reciprocal of that base, which is base 2, and of course maintaining the same two translations, 3 units to the right and 1 unit down.